Hi, my name is Chris Murphy, and in this video, you're going to learn how to rank carboxyl acidity. When you rank carboxyl acidity, start out by looking at the hydroxyl hydrogen. That's the hydrogen that's going to be the most acidic. It can fairly easily be deprotonated, and when it's deprotonated, it leaves behind a negatively charged carboxylate. When it comes to ranking acid strength in general, you want to look at the stability of the conjugate base. The more stable the conjugate base, the better the acid. So when we look at ethanoic acid, it's that hydroxyl hydrogen that's acidic. When it gets deprotonated, it leaves behind our negatively charged carboxylate. And then consider what's going to make this stable. Our electrons can actually move. So there's going to be some delocalization between our two electronegative oxygens. And allowing those electrons to move around more, it gives them more space. And electrons all being negatively charged, the more spread out they can get, the more stable the molecule overall is going to be. So one thing to look for when generally trying to rank acidity strength is how stable is the conjugate base. So look for resonance and delocalization of those electrons to gauge general acidity strength. Another thing that can help you gauge general acidity strength are pKa values. Carboxylic acids have pKa values around 5, so about 4.8 to 4.9. And also note that the lower the pKa, the better the acid. So things like HCl, H2SO4, those are very strong acids and have negative pKa's. A terrible acid like an alkane has a pKa around 50. So if we're comparing acidity between our alkane versus our carboxylic acid functional group, we're looking at a pKa of 50 compared to a pKa of 5. That's an order of magnitude difference of about 10 to the 45th power. So just having that delocalization of those electrons on the conjugate base makes a huge difference when it comes to acidity. Although carboxylic acids generally have their pKa's around 5, the specific pKa and the acidity is going to depend upon what substituents are attached to the molecule. The influence of those substituents on the molecule and its acidity is something called the inductive effect. This is going to be determined by the proximity between the hydroxyl group and those substituents, the type of substituents we have, and then also how many of that type of substituent. One type is going to be electron withdrawing. These electron withdrawing groups are going to stabilize the negative charge, and then that increases the acidity. So if you put a fluorine onto a carboxylic acid, that's going to have an electron withdrawing effect because it's so electronegative. When we deprotonate the hydroxyl group, we're going to be pulling electron density away from that carboxylate. And as you saw earlier, the more electrons can spread out, the more stable the molecule. And the more stable our conjugate base, the more acidic the acid. You can also add more electron withdrawing groups. So if you compare one fluorine to 3 fluorines attached to a carboxylic acid, 3 fluorines are going to pull electron density away from that hydroxyl group even more than if we just had the 1. As a result, 3 fluorines pulling more electron density away is going to stabilize the carboxylate of this carboxylic acid even more and make it even more acidic than if we just had the 1 fluorine. Another factor to consider is the proximity between those electron withdrawing groups and that hydroxyl hydrogen. Here there's 1, 2, 3 carbons between the fluorine and the hydroxyl hydrogen. And if you compare that to having 1, 2, 3, 4 carbons between the hydroxyl hydrogen and the fluorine, there's going to be a difference between the influence the fluorine has on that hydroxyl hydrogen. If the fluorine is farther away, it's not going to pull electrons as hard than if it's going to be closer as it is on the one on the left. So if you rank the acidity between these two molecules, the one on the left is going to be a stronger acid because the fluorine has a larger effect. So you've only seen examples with fluorine so far, and you might be wondering what happens if we change that type of substituent. So if we compare a fluorine to a chlorine, they're the same distance away, but their electronegativities are different. Fluorine being more electronegative is going to pull electrons harder away from the hydroxyl hydrogen than if it was chlorine. So between these two, the molecule with fluorine is going to be a stronger carboxylic acid. So to recap, when we're looking at substituents, the more electron withdrawing groups you have, the stronger the acid. The closer that electron withdrawing group is to that acidic proton, the stronger the acid. And the stronger the electron withdrawing group, the more acidic it's going to be. So if electron withdrawing groups increase acidity, you probably already have guessed that electron donating groups are going to have the opposite effect. They're going to destabilize the negative charge on the carboxylate, and therefore decrease the acidity. Alkyl groups are pretty common electron donating groups. These are going to be carbons with hydrogens attached to them, and if we compare having one carbon to two carbons with hydrogens attached to them, the two carbons are going to push more electron density towards the carboxylate than if we just had the one. So by pushing more electrons towards the carboxylate, it's going to destabilize electrons more, making it a worse acid. So in comparing these two, having only the one alkyl group is going to make it more acidic. So now it's time to put this all together and practice with a question. All right, rank the following carboxylic acids in order of increasing acidity. You have 4-fluoro-3-nitrohexanoic acid, 3,4-dimethyl-hexanoic acid, hexanoic acid, and 4-fluorohexanoic acid. A great place for you to start on a question like this would be to just draw them out, see what they have in common, and see what's different. So go ahead and draw out these four molecules and see what they have in common. It looks like they all have a parent chain of hexanoic acid, so we can start there. Hexanoic acid is going to have 6 carbons and a carboxylic acid group at the end, so it looks something like this. The next thing you're going to want to do is draw out the substituents, and then we'll see what effect they're going to have on the acidity. In molecule A, you have a 3-nitro group and a 4-fluoro group. Molecule B, you have 2 methyl groups on carbons 3 and 4. Molecule C is already hexanoic acid, there's no other substituents. And molecule D just has a fluorine on carbon 4. So now if you focus in on those substituents, you're going to want to consider if they're electron withdrawing or electron donating. And remember that electron withdrawing groups increase acidity, electron donating groups are going to decrease acidity. So if you take a look at molecule A, we have a nitro group. There's a nitrogen with 2 oxygens, both electronegative and electron withdrawing, so they're going to be pulling electrons away from the carboxylic acid group. We have a fluorine, also electronegative and pulling electrons away from the hydroxyl group on the carboxylic acid. Molecule B has our 2 methyl groups, and if you remember, methyl groups are going to be electron donating, so they're going to be pushing electrons toward the hydroxyl group. Molecule C doesn't have any substituents, and molecule D has our fluorine, which you already saw is going to be electron withdrawing. So now if you go through and rank these molecules in order of increasing acidity, the weakest acid is going to be the one with the electron donating groups, which is molecule B. Just above that's going to be molecule C. It doesn't have any donating or withdrawing groups in comparison to the other molecules. Then we have molecule D with 1 electron withdrawing group, and the most acidic is molecule A with 2 electron withdrawing groups. So ultimately, the things to keep in mind when you're ranking carboxylic acids is electron withdrawing groups are going to be increasing their acidity, electron donating groups are going to be decreasing acidity. And it all comes down to the stability of the conjugate base once that proton is removed. The more stable the conjugate base, the more acidic the acid.